This video is on applying Newton's second law of motion to coupled systems. So coupled systems is pretty much two objects or more objects connected to each other by strings, massless strings. Question 1. A block with the mass of 2 kilograms is on a rough horizontal surface with a coefficient of friction 0.4. Attached to the right of M2 is a massless string which is pulling M2 to the right with the force of tension Ft. Attached to the right of the massless string is another block of mass M1 equals 30 kilograms. Attached to the right of M1 is another massless string which pulls the whole system with a constant pulling force of 800 newtons and constant acceleration A. Part A, draw a free body diagram. Remember, circle the objects, label the forces, put an X and Y axis, and use Newton's second law, F equals ma. So we're not going to draw one big circle. We're going to draw two circles, one for each object. This means for each circle, when we apply Newton's second law, F equals ma, we could only apply it to the forces inside one of those circles. We cannot use sigma F equals ma on forces in both circles. So here I've clearly labeled the forces on on both objects. Part B, find the acceleration of the whole system A. So we have two objects. Each object is going to have the equation sigma F equals ma on the x-axis and on the y-axis. So this is sigma F equals ma on the y-axis. We find force normal 2. This is sigma F equals ma on the x-axis. This is sigma F equals ma on the y-axis for object 1, mass 1. This is sigma F equals ma on the x-axis for mass 1. So we have these two equations here in yellow and green. We know a sub x1 equals a sub x2 equals a. They accelerate at the same rate because they're attached to each other. So let's add this yellow and green equation, solve for acceleration, we get 12.1 meters over second squared. Part B, find the force of tension of the massless string which attaches both masses. So we have this yellow equation, solve for force tension. Question 2, Atwood's machine. A massless frictionless pulley is attached to a ceiling. Mass M1 is 16 kilograms, is at rest on the ground. It is attached to a massless string which is over the massless frictionless pulley and is attached to another mass M2 equals 46 kilograms, which is also initially at rest in the air. M2 is released from rest and both masses accelerate at a constant rate. Part A, draw a free body diagram. This is our free body diagram. Remember, step 1 is to circle the objects. We have two objects. Step 2, label the forces. Step 3, put an X and Y axis. And step 4, use the equation F equals ma. Two things. Number 1, I didn't put a force normal on mass 1. Why is there no force normal on mass 1? Because the moment you release mass 2, mass 1 leaves the surface. And force normal is a contact force. It only exists if two objects are touching each other. Second thing to observe, I let the positive x-axis be clockwise. So if mass 2 goes down and mass 1 goes up, that's positive x. If mass 1 goes down and mass 2 goes up, that's negative x. So this way we decrease the number of negative signs. Part B, find the common acceleration of the system. For mass 1, sigma F equals ma. force tension minus force gravity equals ma. Why? Because for mass 1, force tension up is making the object go in the positive direction. Force gravity down is making the object move in the negative direction. For mass 2, we have force gravity minus force tension equals ma. So you could see the force of gravity makes mass 2 go down, force tension makes mass 2 go up. So we have this equation. We know A1 equals A2 equals A, and we know force tension 1 equals force tension 2 equals force tension because it's the same string. Let's take the yellow and green equation and add them both up to eliminate force of tension, because we have two equations, two unknowns, right? Solve for A, we get 4.75 meters over second squared. Part C, find the force of tension in the massless string. Just substitute back into the yellow equation. Question 3. A block of mass m1 equals 12 kilograms sits at rest on a horizontal surface with mu equals 0.24. Mass m1 is attached to a massless string which goes over a massless pulley, which is attached to another block of mass m2 equals 36 kilograms. Part A, draw a free body diagram. Remember the 4 steps. Circle the objects, label the forces, put an x and y axis, and use the equation F equals ma. So I circled 2 objects. I labeled the forces on 2 objects. I put an x and y axis, and here you could see positive x is clockwise. So if mass 2 goes down and mass 1 goes to the right, we have positive x. If mass 2 goes up and m1 goes to the left, then we have negative x. And positive y only applies to mass 1. So remember, we circled the object because when we use F equals ma, we could only use that for one circle. We cannot use sigma F equals ma for forces on both circles. Part B, what is a common acceleration of the blocks? Look at mass m1 first, this one on the surface. For the y-axis, we have plus force normal minus force of gravity here. And that's equal to 0 newtons because the object is not jumping up and down. On the x-axis, we have plus force of tension minus force friction for mass 1. So that's what we have here. Now take a look at object 2. Sigma F sub x equals ma sub x. We have plus force of gravity minus force of tension. So we know force of tension 1 equals force of tension 2. We'll call that force tension. We know a sub x1 equals a sub x2, which is acceleration. So we have 2 equations and 2 unknowns. We don't know acceleration, we don't know force tension. Let's add these 2 highlighted equations. And we eliminate force tension, we solve for acceleration. Now we know acceleration, let's substitute into the yellow equation to get force tension. Question 4. This is something you really have to know because this is like a classic physics problem. A 4 kilogram mass m1 is initially at rest on a theta equals 30 degree incline. The surface has a coefficient of friction mu equals 0.4. The 4 kilogram mass has a massless string attached to it, which goes over the top of the incline above a frictionless pulley to another mass m2, 18 kilograms, which is hanging in the air. Both objects are released from rest and move with a constant acceleration. M2 moves down while M1 moves up the incline. Part A, draw a free body diagram. So remember what I said, circle the objects, label the forces, put an x and y axis, and use F equals ma. So I did not circle the objects, but there are two objects. I labeled the forces, I put an x and y axis. So notice my x-axis is counterclockwise. That means if m1 goes up the incline and m2 goes down, we have positive x. If m1 goes down the incline and m2 goes up, then we have negative x. And positive y is 90 degrees from the surface of the incline. So positive y only applies to mass 1. You could see I did this because I want to minimize sines and cosines. Force normal 1 is purely in the positive y direction. Force tension 1 is purely in the positive x direction. Force friction 1 is purely in the negative x direction. And force of gravity 1 has a component in both the x and y direction. So let's take a look at mass 1, which is on the incline. Sigma Fy1 equals m1 Ay1. We know Ay1 is 0 because this object on the incline is not jumping up and down. So force normal 1 minus Fg1 cosine theta is equal to 0 newtons. Why is it cosine? It's because this y part here is a cosine part, the vertical part. So we get this equation. Let's take a look at mass m1 again. Let's take a look at the forces on the horizontal axis, the x-axis. So we got plus force tension 1 minus force of friction 1 minus Fg sine theta. Why is it sine theta? Because we got this here. Here's theta, here's sine of theta. This should say Fg1 sine of theta equals m1 a sub x1. Force of friction is mu force normal. Force of gravity is mg. And we have this equation in yellow. Let's take a look at mass 2. Sigma F sub x2 equals m2 a sub x2. Force gravity 2 is positive. Force of tension 2 is negative. Force of gravity 2 is m2g. So we know force tension 1 equals force tension 2 equals force tension because it's the same string. A sub x1 equals a sub y2 equals a. Because they both accelerate with the same magnitude. So we have the yellow equation and the green equation. Let's add them both up. We get this. Let's solve for a. Acceleration, we get 6.52 meters over second squared. What would be the force of tension on the string? Substitute this acceleration to the green equation, and we could solve for force tension. So, part A tells us to draw a free body diagram. We did. Part B asks for the common acceleration of the objects. The common acceleration is here. Part C asks for the force of tension on the string. The force of tension on the string is here in part D. So C and D are the same. Question 5. A block which has a mass m2 equals 8 kilogram is held at rest on a rough horizontal table, which has a coefficient of friction of mu equals 0.2. It is attached by a string to a mass m3, which has a mass of 14 kilograms, which hangs to the right of the table, and another string to a mass m1, which hangs to the left of the table, as shown below. Mass M2 is released from rest and the whole system accelerates with a constant rate. So what happens? M1 goes up, M2 goes to the right, and M3 goes down. So part A, draw a free body diagram. So remember, step 1, circle the objects. Step 2, label the forces. Step 3, put an X and Y axis. Step 4, use the equation F equals ma. I did not circle the 3 objects. Forgive me. That's step 1. Step 2, label the forces. I labeled all the forces. Step 3, put an X and Y axis. I said positive X is clockwise. So if M1, M2, and M3 move in a clockwise direction, that's positive X. If M3, M2, and M1 move in a counterclockwise direction, that's the negative X axis. And positive Y only applies to mass 2. Part B, determine the acceleration of the system. So parts B and C will be solved simultaneously because part C wants us to find force of tension 1, 2 and force of tension 2, 3. Force of tension 1, 2 is a force of tension on the string which connects mass 1 and mass 2. Force of tension 2, 3 is a string which connects mass 2 and mass 3. So, for mass 1, sigma F sub x1 equals m1 a sub x1, which is force of tension minus force of gravity. So that's here on the left side, mass 1, plus force of tension minus force of gravity. We got that here. For mass 2, on the x-axis, we have plus force of tension minus force of tension minus force of friction equals m2a sub x2. Look at this object which is on the table. We have plus force of tension 2, 3 minus force of tension 1, 2 minus force of friction. That's how we get this here. And we know force of friction equals mu Fn. And here we have sigma F sub y equals ma sub y for mass 2. This is not jumping up and down, so we know force normal 2 minus force gravity 2 equals 0, which is here. And finally for mass 3 we have F sub g minus F of t, force of gravity minus force tension equals ma. Look at mass 3 here. Force of gravity plus force of gravity minus force tension equals m3a3. Okay. So we have 3 equations, yellow, green, and blue. So we now have 3 equations and 3 unknowns. Substitute the yellow and blue equation into the green equation. So when we do that, we only have 1 equation, 1 unknown. The unknown is acceleration. So the acceleration is about 4.25. Substitute the acceleration into the yellow and blue highlighted equations to solve for ft12 and ft23. So we've solved for force tension 1, 2, force tension 2, 3, and acceleration. Question 6. An object of mass m1 equals 2 kilograms is sitting in a horizontal plane. It is connected to another object with mass m2 equals 9 kilograms by a massless string which goes over a massless pulley. The coefficient of friction between the 2 masses and the surface is 0.15. Mass m2 is on an inclined plane which is 30 degrees below the horizontal. So part A, label the forces on each object. So remember, 4 steps. Tell me the 4 steps. Step 1, circle the objects. Step 2, label the forces. Step 3, put an x and y axis. Step 4, use the equation F equals ma. So you could see positive x is clockwise, and for mass 2, positive y is 90 degrees from the surface. Part B, determine the common acceleration of the two blocks and the force of tension in the massless string. So you could see what I did here on the top left. I use sigma f sub y equals m sub 1 a sub y for object 1, which is here, which is the one that's on the horizontal surface. So plus force of normal minus force of gravity equals 0 here, because acceleration is 0. For the horizontal axis, I have plus force of tension minus force of friction equals ma. Plus force of tension minus force of friction equals ma. And force of friction equals mu force normal. And what is force normal? It's m1g. So I substitute that here. Take a look at mass 2. What's on the x-axis? We have plus force of gravity sine of theta minus force of tension. That's here. Plus force of gravity sine of theta minus force of tension minus force of friction. So there's a minus force of friction minus force of tension. That's here. Now here on the bottom left, I solved for plus force normal. So look at the two highlighted yellow equations. We know a sub x1 equals a sub x2 equals a. And we know force of tension 1 equals force of tension 2 equals force of tension. This is a small mistake. A sub x1 equals a sub x2 equals a. F sub t1 equals F sub t2 equals force of tension. So we have these two highlighted equations. Add them up. We're going to eliminate force of tension. We only get A. A is about 2.70 meters over second squared. Now we could substitute this acceleration to one of these yellow equations to get force of tension. Question 7. An object of mass m1 equals 2 kilograms is sitting in an inclined plane in which theta 1 equals 45 degrees. It is connected to another object with mass m2 equals 14 kilograms by a massless string which goes over a frictionless massless pulley. The coefficient of friction between the two masses and the surface is mu equals 0.150. Mass m2 is on an inclined plane in which theta 2 is 30 degrees. Part A, label the forces on each object. So could you tell me the 4 rules for free body diagrams? Step 1, circle the objects. Step 2, label the forces. Step 3, draw an x and y axis. Step 4, use the equation F equals ma for each object. So you could see step 1, I circled the 2 objects. Step 2, I labeled the forces on both objects. Step 3, I put an x and y axis. So I'm doing good. You could see positive x is clockwise. So if m2 goes down and m1 goes up, that's positive x. If m2 goes up and m1 goes down, that's negative x. Part B, determine the common acceleration of the two blocks and the force of tension in the massless string. So you have to see what I did here. In this first column here that I highlighted, this is only for mass 1. So this is for the y-axis. This is for the x-axis. This here is for the y-axis for mass 2. This here is for the x-axis for mass 2. We know that they have the same acceleration and the same force of tension, so that gets rid of some variables. So now we have these two equations. Add them up. We could eliminate force tension, we could solve for acceleration. And then we could substitute back into one of the original equations to solve for force tension. Question 8. A block with mass m2 is pulled to the right with the force of pull. Another block with mass m1 sits above m2. The coefficient of dynamic friction between the two blocks are mu12, and the coefficient of dynamic friction between m2 and the surface is mu2s. Part A, label the forces on each object. So for m1, these are the forces on m1. I did not circle the objects, I apologize. For m2, these are the forces on m2. So once again, these are the forces on m1. And these are the forces on m2. Part B, determine an equation for the magnitude of the acceleration of each block and the force of tension in the massless string in terms of m1, m2, mu1, 2, mu2 surface, force, pull, and g. So we want the acceleration. So this is sigma f sub y1. This is sigma f sub x1. This is sigma f sub y2. This is sigma f sub x2. So definitely pause the video and try to see how I obtain these equations. So I'm going to let positive x be when m2 goes to the right and m1 goes to the left. Negative x is when m1 goes to the right and m2 goes to the left. So a sub x1 equals a sub x2 equals a, force of t1 equals force of t2 equals force of t. So now the two blue equations become this. I called a sub x. Add up the two equations above, and we get this. The left side plus the left side equals the right side plus the right side. And then I solve for acceleration. So here's my equation for acceleration. We could also solve for force tension. So the problem only wants to solve for acceleration and force of tension. So a lot of this is just algebra. Here's A, acceleration. Here's force of tension.